You've probably looked at some huge piece of software and wondered, how on earth does this not just completely fall apart? I mean, millions of lines of code. Well, the answer, the secret sauce, is something called object-oriented programming. And today, we're going to pull back the curtain and show you exactly how it works. Seriously, it's a fair question. How do developers build these massive, complex applications and, keep it all straight? The secret isn't just about hammering out more code, it's about thinking about code in a fundamentally smarter way. And that smarter way is all about this, thinking in objects. Instead of writing one giant list of instructions, we start to model our code after the real world. We create things, objects, like a user or a car or a product. And this one simple shift in perspective is what makes managing all that complexity not just possible, but actually pretty elegant. So how do we start thinking this way? Where do we even begin? Well, it all kicks off with the very first pillar of OOP, the idea of creating blueprints. Okay, this right here is the absolute core of it. A class in Python is just like a blueprint for a house. It's not the house itself, right? It's the detailed plan that says every house built from this plan must have a door, 2 windows, and a roof. It defines the structure and the rules. So naturally, if the class is the blueprint, then an object is the actual house you build from it. It's the real thing you can see and interact with. We call this an instance of a class. This is so powerful because from one single car blueprint, you can create thousands of individual car objects, each one a unique instance with its own color and mileage. And here's how that looks in actual Python code, broken down into 3 simple steps. First, you lay down the blueprint using the class keyword. Easy enough. Second, you create this special __init method. Think of this as the initial setup instructions. When you build a car object, this is what runs to give it its brand and model. And third, you actually build it. Just like that, my car is a real, living car object, an instance, fresh off the assembly line. All right, so we can create objects from blueprints. That's a fantastic start. But what happens when you need something that's almost like what you've already built, but just a little different? This brings us straight to our second pillar, reusing code. Check this out. It's a super common problem. We have our car class, now we want an electric car class. You can see they share a lot of the same DNA, right? They both have a brand, they both can drive. The temptation is just to copy and paste. But trust me, that way leads to madness. Find a bug in Drive, now you've got to fix it in 2 places. It's a nightmare. So what do? Well, thankfully, there is a much more elegant solution. It's a beautiful concept in OOP called inheritance. The best way to think about it is like a family tree. We can create a more general parent class, let's call it vehicle, that knows how to drive road. Then, our electric car becomes a child class that inherits from vehicle. That means it gets the drive method completely for free, no copy-pasting required. Then, it can add its own special tricks, like a charge method. It's a way of saying an electric car is a kind of vehicle. Okay, so we can create things and we can reuse code. That's huge. But what about making our code more flexible, more dynamic? This leads us to our third and final pillar, adapting behavior. Take a look at this. Just a simple plus symbol. You've seen it a million times, but what does it actually do? Well, the answer is, it depends. I mean, look at this. When you use that plus sign with numbers, it does what you expect. Addition. 3 plus 7 is 10. Simple. But use that exact same symbol with 2 pieces of text, and boom, it does something totally different. It joins them together. Same symbol, different behavior, all based on the context. This little magic trick has a name, and you've actually been using it this whole time without even knowing it. It's called polymorphism, which literally just means many forms. It's this incredibly powerful idea that one name can mean different things for different objects. So you could have a dog object and a cat object, and they both have a speak method. You just tell them both to speak, and polymorphism takes care of making sure one says woof and the other says meow. It's what makes code so incredibly flexible. So blueprints, family trees, shape-shifting symbols, this all might seem a little abstract, right? But what does it all mean in practice? Let's connect these dots to the real-world software you probably use every day. So let's do a quick recap. We've got our 3 pillars: C for classes, which let us create our blueprints, I for inheritance, which lets us reuse our code, and P for polymorphism, which lets our code adapt its behavior, create, Reuse, adapt. That is the heart and soul of object-oriented programming. So why does this all matter? Because this isn't just theory. It's the absolute foundation of the modern Python world. Take a web framework like Django. A user, a blog post, those are classes. A special kind of user, like an admin user, inherits from the basic user class. And the framework uses polymorphism to handle all sorts of different web requests through one common interface. It's everywhere. This is how professional software gets built, period. So there you have it. You now have the fundamental tools of a software architect, the power to create, to reuse, and to adapt your code in a clean, powerful way. The only question left is, what blueprint are you going to design first?